Thanks for invitation. I'm very happy to be here. So maybe I will share my screen now.
Absolutely.
Yeah. Can you see my screen now?
Yes, thanks. Perfect.
Okay, so hello everyone. I'm Yonglong Tian, a PhD student at MIT. So I'm very happy and very honored to be here to share some of my research about contrastive learning. So contrastive learning is a general self-supervised learning approach. So in today's talk, I will try to firstly cover most of the recent state-of-the-art contrastive learning methods and go over them quickly. And then we will dive into my most recent research on how to construct effective views for contrastive learning. Okay, so before we go to self-supervised learning, let's take a look at the traditional supervised learning. So typically given an image, you have a learner, which is typically a neural network, to predict some sort of semantic output of the input data. So here the label is a cat, and such label is typically labeled by human annotators. So in such image classification tasks, it might be easy to have such annotation. But in many tasks, it might be pretty hard. For example, if you want to label every pixel in the autonomous driving scenario, it's pretty hard, and sometimes can be even invisible. So self-supervised learning is, instead of using labels from the people to guide your learner, you somewhat generate some labels automatically from the data. So the Y prime here, you just, it can be any pseudo label that you generated from the data, and you use this Y prime to guide your learner. And such Y prime can be very cheap to obtain, and it without any human annotation. So probably you have been familiar with LeCun's cake analogy about self-supervised learning, where he thinks like the self-supervised learning is really the cake layer, where the data itself provide millions of information bits. So you can use the data to supervise the data itself to learn good representations. So here I roughly divide the previous self-supervised visual representation learning approach in two categories. First is non-contrastive approach. You can see there are many neat ideas there, such as image imprinting, colorization, and predict the rotation of the image. But you can see, yeah, of course, these ideas are very neat, but you can see there is not a very clear link between all these approaches. It's like just some random work inside the methodology space. And for contrastive learning approach, it's a more principled approach. And probably you have noted that here, I put the arrow of contrastive learning higher, a little bit higher than the arrow of non-contrastive learning approaches. This is because I think contrastive learning approach is somewhere between a purely self-supervised learning and supervised learning. And in later slides, we will see that contrastive loss can be both used in self-supervised case and supervised case. So it's a more principled approach. So now let's take a look at the ImageNet unsupervised representation learning benchmark. What people typically do is you firstly train a backbone using self-supervised learning approach. And after that, you freeze your backbone and you just train another linear classifier on top of the frozen representation to see how linearly separable these representations are. Of course, this is definitely not a perfect measure, but it somewhat tells us how much semantics the latent representation captures about. So this is the progress before contrastive learning. So you can see we are making steady progress, but it's pretty slow. And in the year of 2018, contrastive approaches jump in, and then it just improves the state of the art very quickly. And remember that the current state of the art, the best performing supervised method with the biggest model on ImageNet is roughly about 85 or 86. So you can see here, yeah, maybe move a bit. So you can see here, the unsupervised approach can already touch 80%. So it's pretty close and pretty crazy. So now let's take a look at what is contrastive learning. The idea is generally pretty simple. You just try to pull together similar pairs and push away dissimilar pairs. There are multiple formats of such contrastive learning. So in the year of 26, in LeCun's paper, Dimensionality Reduction by Learning and Environment Mapping, they provide the initial idea of contrastive learning, where they say that, okay, the distance of a similar pair should be lower than a certain threshold, while the distance of dissimilar pairs should be larger than that threshold, but you have to set that threshold manually. And later on, there are like other loss, like a triplet loss. But the thing is, like you really have to do hard negative mining over the for triplets, because you can. It's very easy for us to get not informative negatives. And the most recent approach for contrastive learning is actually the unpaired loss. So what is the unpaired loss? Now let's take a look at the unpaired loss. It's pretty simple here, the idea actually. So without loss of generality, let's assume we have a pair of variables, x and y. And x, I, and yi are paired data. So it's kind of, you can think of it as you get some samples from the joint distribution. And now, given the anchor x3 on the left, you want to find its corresponding y sample on the right side. And of course, it's y3 here, right? And so x3 and y3 are similar pairs, but x3 and all other y's are dissimilar pairs. So therefore, you are trying to discriminate samples from this joint distribution with samples from product of marginals. But typically, such data set in such N can be very big. So for example, in ImageNet, N can be 1 million, so you cannot put everything in one single batch. So what people do is to subsample k negatives. So it's also simple. You just randomly subsample k negatives. K is typically like several thousands. And then given this x and y's, how do you construct the contrastive loss? It's also pretty simple. So the general idea is you treat the x3 as the anchor point, and you try to find the only corresponding positive y3 out from k distractors in a softmax format. So you kind of perform, you have a similarity function to measure how similar each pair is, and you have a softmax function. It's pretty simple. And so now let's take a look at the image contrastive representation learning. What has been typically done here is you have, so here in this example, you have 2 images. For each of the 2 images, you have 2 augmentations. So one augmentation is treated as X, and another augmentation is treated as Y, so that you are trying to repair crops from a different image while pulling together 2 augmentations of the same image. So the idea is simple, just use data augmentation. And the second caveat about image contrastive learning is you really need large number of negatives. This figure is from the MoCo paper. So you can see for the x-axis is the number of negatives you use to contrast each positive pair. You really need large number of negatives to make it saturate. So the question is really how to make large number of negatives feasible. And there are three previous mechanisms, which is a memory bank, moment encoder, and large batch. So we will go over this three quickly. So in summary of these slides, for contrastive learning, there are really two things. First is how to define the two views, X and Y. And the second is how to have large number of negatives. Okay, so this is the instance discrimination paper, which in my opinion is the open chapter of modern contrastive learning approaches. So what the author do is maintain a so-called memory bank. So the memory bank is the space complexity of the memory bank is ON. N is your data set size. So for ImageNet, So for ImageNet, it's 1 million, and it's pretty large, right? So what the author does is, okay, so they have an image as input, so you can do a random crop over this image to get an augmentation, and you extract the feature xi as your anchor point. Now, you know the index of the image, so you can go to the memory bank and retrieve the corresponding feature vector yi for the same image, and retrieve at the same time retrieve large number of negatives, I mean y negative from other images, and you perform contrastive loss. So the key is actually how to maintain such a memory bank. Well, so you can imagine that the most you can do is every epoch you compute the feature of the image xi, and you push this xi into the memory bank. But in that case, you will only update the memory bank once per epoch. In other words, the memory bank is updated very slowly, and the earliest item in the memory bank and the latest item in the memory bank, they can have very different distribution. So you really have to maintain the stationarity of this the features in the memory bank. So how to do it is you have some momentum update. So you update the memory by, okay, combine some sort of the current feature and some sort of the EMA from the previous epochs. So that's the trick in this paper. And without this trick, the contrastive loss just doesn't work. So you can see the importance of maintaining such a stationary distribution of the feature. And therefore, in the MoCo paper, but you can see one drawback here, one drawback in the memory bank is the space complexity is, is proportional to your data set size. So imagine if you have really large data set, you have to scale up the memory bank as well. That's a drawback. To overcome this drawback, the momentum encoder provides another idea, which is using the moment encoder such that you can maintain a fixed size memory cache. So as I mentioned before, for the memory bank, the key is to maintain the momentum update of the features inside of the memory bank. The MoCo paper actually transfer the momentum update on the feature bank to the momentum update on the parameters of the encoder. So what they do is they have two images, and they have one image, they have two different crops, and this is an online encoder that help you get the anchor feature point xi, and the momentum encoder is updated very slowly, so that features extracted by this momentum encoder will mostly be stationary. The distribution of the features will not change significantly. Therefore, you can use the momentum encoder to compute the yi on the fly. At every batch, you will enqueue the most recent features yi into the queue and dequeue the earliest features so that the queue is maintained with a fixed size. but you cannot retrieve the feature of specific image from the queue because you don't maintain the index there. But the next thing is, okay, now you can scale up to really large data set with the queue to be fixed size. And of course, the key is to maintain the moment update of the parameters of the moment encoder. So it's pretty similar to the incidence discrimination paper, but the two papers maintain the stationarity to maintain the features to be stationary from different perspective. And okay, if you are Google, you can easily overcome this non-stationary property of the feature by just having a big large batch. Then every feature is computed on the fly using the same parameters. Then the features are just the distribution are the same, and you can directly perform contrastive loss. And there are other sort of contrastive learning approaches which try to have large number of negatives, but with a small batch size. So how do people do this in the CPC paper and AMDIM paper? Well, they have one image. They also have two different augmented views. What they do is actually they use the global feature for the left image as the first view. And for the second view, they don't use the global feature. Instead, they use a lot of local features. So in that case, you can really have a lot of positive pair and a lot of negative pair, even though your batch size is small. So for example, if the feature map size is H and W, then you use the feature pair from the same image as a positive pair, while you use feature pair from different images as negatives. Then you can see you can easily build B minus 1 multiply H multiply W, such big number of negatives with a small batch size B. So it's pretty neat. But the thing is, one caveat about this approach is you have H multiply W negatives per image. So you hope those features are not very similar. They are not saying, otherwise the effective number of negatives might be. So otherwise imagine if every feature point here is pretty similar, then the H multiply W, actually they are not really such number of effective negatives. Most of the negatives are pretty similar and duplicate, and then that doesn't make sense. So the caveat of this approach is you have to maintain a small receptive field of each local feature descriptor, such that each local feature descriptor is describing different local patches. Okay, so now let's take a look at another stuff. This is a joint work with my co-author Denip and Philip. So instead of trying to just use data augmentation as two different views of the for contrastive learning, compared with the previous approaches, we thought about this problem from an orthogonal perspective. We thought, okay, maybe you can just use any of those previous approaches to build a large number of negatives, but it's very important to construct views. So for example, here in this approach, we can decompose one image into chrominance and luminance, so that we use two different modalities to do the contrastive learning. The insight behind is we are hypothesizing that useful information bits are typically shared between different modalities, and modality-specific information bits tend to be noise. So if you have multi-modalities and you use contrastive learning between those modalities, it will just help the representation emphasize on information bits that are shared across the different modalities. In that way, it will extract higher level semantics information rather than focus on modality specific details. And we found that this approach can outperform MoCo and the instance discrimination with the same architecture and the same number of negatives. So you can see the benefits of have construct different views. And of course, you can use RGB as one view and optical flow as the other view, and you do contrastive learning. And we can use this and outperform other methods on UCF 101 using the same backbone architecture. And of course, you can go beyond two views. You can have multiple modality at the same time. The hypothesis is if one information bit is shared by all of the views and all different modalities, that information bit should be important. And you should emphasize on that bit. And if one information bit is only shared, it's not shared, it's only contained in one specific modality, okay, it tends to be noise. So you can imagine the case that how human perceive a dog inside a room. So you can see the dog, you can visually see the dog, and you can hear the dog voice, and you can sometimes even smell the dog. So the information bits of dog is higher semantic and is shared by all of the three different modalities, but the camera angle is only shared inside the visual modality, and probably is not that important for higher level semantics of recognizing the dog. And the nice thing of this is we found as you increase the number of views, the representation quality of each single view gets improved. And of course, so for the contrastive learning approach, you can have more examples to construct the different view pairs, X and Y. For example, you can have visual and audio to form the pair to do contrastive learning. You can have visual and text, and you can have different languages, to do the contrastive learning as well. So the idea is pretty general, and you can have different applications here. So then the next question to me is, okay, instead of just using different augmentations from the same image as two views for contrastive learning, what are other important properties for constructing good views? So that's the question we are trying to answer and trying to just dig a bit. So in order to get into it, we first need to get back to the mutual information interpretation of contrastive learning. So as we discussed before, the contrastive objective is really trying to discriminate between samples from the joint distribution and samples from product of marginals. So it's really have some natural collection with mutual information between the two views. Instead, actually, minimizing the contrastive loss is trying to maximize lower mutual information bound, which is called the NCE mutual information bound. So you can see minimize the contrastive loss equals to maximize mutual information between two views. So that is to say you are trying to contain the information bits that are shared by two views. You are trying to square those information bits into the latent representation. So yeah, so from the information diagram, you have two views, V1 and V2, and the mutual information is the overlapped region between them. And the contrastive learning approach is really trying to leverage this bits of information. So therefore, what are good views for downstream task? There is some theoretical claim in our paper here. So it's actually not, it's actually 2020, not 25. It's just from this year, several months ago, sorry. So we have some theoretical claims there, but to just have a gist of it, So it's suppose you have a downstream task which has label Y. This is some downstream task. Suppose we know the label Y. And then when you construct V1 and V2, two views from the input data tensor X. So for example, X can be image, and V1 and V2 are two augmentations of X. And also, X can be the joint tensor of audio and visual, and V1 can be the visual part, and V2 can be the audio part. So V1 and V2 is a function of the complete tensor X, okay? So the thing is, you really need to keep all information that X has about Y into X1, into V1 and V2. So basically, says when you split the tensor, you hope each view will contain enough information that X has about Y. At the same time, you want to remove task irrelevant information. That is to say, you want the mutual information between V1 and V2 is minimized. So you want to remove all of those non-irrelevant information. So from the information, this is what we call the informing principle. It means you want to construct those two views such that the mutual information is only about your downstream task Y. So from the information diagram, so this is your V1 and V2. So you hope your information of Y is not contained just by V1, it's not just contained by V2, it's just right here in the overlapped region shared by both V1 and V2. So in that way, contrastive learning will just leverage the information about the Y to construct the representation. And we have a hypothesis about this. So you can imagine that when we construct the V1 and V2, we can have the V1 and V2 that doesn't share any mutual information. So V1 cannot predict any part of V2, and V2 can also not predict any part of V1. And you can imagine in that case, the contrastive noise cannot do anything. The mutual information between them is zero, that is to say, the samples from the joint distribution and say samples from the product of marginals are not differentiable. You cannot tell the difference. So then we can try to gradually fill in information bits between V1 and V2. And of course, there are infinitely many ways to fill information bits. For example, you can firstly fill in task relevant information bits and then fill in noise. Or the other way, you can fill in noise first and then task relevant information. So it's plenty of ways. So here we think about from an optimal way where we firstly fill in all the task relevant information bits until we touch the limit. That is Ix and Y, Ixy. And after that, we cannot fill in other task relevant information bits because all have been filled in. The next, we can only fill in noise. So in this case, this traces this trajectory. You can imagine at the very beginning, we are filling task relevant information bits. Then you get more and more information about the downstream task. And for the transfer performance, it's just keep improving. And after you touch this sweet spot, if you keep filling information bits, you can only fill in noise or task irrelevant information. And in that case, you are just filling noise at the signal noise ratio is decreasing. So you can imagine the transfer performance starts to decrease. So here you can imagine such a reverse U-shape. If you contain too much information between these two views, you have too much noise and the transfer performance is bad. If you don't have any information shared between them, that's also bad too. The contrastive learning doesn't work. Can't have anything. You just should have the right amount of information and the right information bits there. So this is a reverse U-shape. Now let's take a look at a toy example to understand this property. So we construct, to understand this property, we construct a moving MNIST data set where you have canvas, image canvas, and the digit is moving constantly with constant speed inside the canvas. And the digit will bounce off when it touches the boundary. So therefore, you can imagine that once you know the first few frames of the digit, you can infer the speed of the digit. And therefore, you can deterministically decide where the digit should be in future frames. Okay. So let's have a sequence from x1 to xt, and we just use the first k frames as the first view, the view 1. And to construct the second view, we construct the second view by referring to the xt frame. So for example, we can use the digit position in the xt to construct another v2. So you can see here in this example, the digit position of the v2 plus is the same as xt, but the digit and the background image are random sample. Therefore, the mutual information between v2 and the xt is only the digit position. And because v1 can deterministically predict the position of digit in xt, so therefore, the mutual information between v1 and v2 is actually about the digit position. Similarly, you can construct v2 plus in ways such that the mutual information between v1 and v2 is only the digit, or the mutual information between them is v1 and v2 here is just the background image. The digit and digit position are randomly sampled. Okay, so now you really construct many different views. Oh, sorry. So just give me a second. I didn't have this animation. Sorry. Okay. Now let's take a look at the case where we have two views. So for example, you can have the two views to just share one single factor. So if in this case, if they just share the digital information and you extract the representation by contrastive learning, and on top of the representation learned by contrastive learning, you have a different classification head to do several tasks. The first is you predict the digit class. The second is you predict the background class. Okay, the background image is from the STL10 dataset. So you have 10 background classes. And you predict you regress the digit position. So you have 3 tasks, and you are using the 3 tasks to evaluate the representation. So if V1 and V2 only share digital information, okay, it performs well for the digital classification. So here's the error rate, lower the better. But it doesn't perform well for background classification and the digital localization. And similarly, if you just share the background information, okay, it will do good for the background classification, but cannot do good for digital classification. So if V1 and V2 share the post information, so the learned representation will be good at predicting the position of the digit, but not the other 2 tasks. So things are more interesting when V1 and V2 contain multiple factors, because people might imagine, okay, if V1 and V2 shares all of the 3 factors, then the learned representation might perform well for all of the 3 tasks. Actually, it turns out not to be the case. So if you share V1 and V2 share all of the 3 factors here, it just perform good for the background classification. It doesn't perform good for other 2 tasks. Basically, just for digital classification, it's just a random guess. So the thing is actually, when you have really a lot of information bits there, background is a dominant factor. It will overwhelm the other 2. so that your contrastive learning objective will not use the digit and position information to solve your task, solve the contrastive task. It will only leverage the background information because that's some sort of shortcut. And then your representation only captures the background property and forget about things about the digit and position. So that's how you can see if you contain too much information there, it just sucks for like the task of digit classification. Okay, so let's take a look at a more practical case where in previous discussion we are saying, okay, if you know your downstream task, what your downstream task is, you can try to reduce the mutual information between those two views to a property amount to get good representation for your downstream task. But in most cases, you don't know the downstream task beforehand. So the question is really is, can we blindly reduce the mutual information between two views to achieve better representation? So the answer actually is yes. So in this example, what we do is we extract two patches from the same image to construct a positive pair. You can imagine we can control the distance between these two patches. If they are closer enough, the mutual information between them is higher. If they are further away, the mutual information between them is lower. So in that case, you can control the mutual information between them by control the distance between them. So in the right plot, the number here is actually the distance between the two patches. Remember the patch size is 64. So the distance of 64 is the closest of non-overlapped region. So it's just close to each other. And you can see as you gradually increase the patch distance, you can see the x-axis is the neural mutual information estimation. You increase the patch distance, the mutual information get decreased. This is aligned with the theory side. But the interesting thing is, if they contain too much mutual information, your transferring performance is not good. There is such a sweet spot here. You don't have too much mutual information. You don't have too less. You just have the right amount of mutual information that makes the transferring performance optimal. And another example is you can leverage kernel space to construct two views. For example, you transfer RGB image into a specific kernel space and you create two views by splitting over the channel dimension. For example, you can use the first channel as one view and the remaining two channel as the other view to do contrastive learning. So with a different kernel space, you can also see this reverse U-shape. So firstly, as you reduce the mutual information, the transferring performance get improved. But here the difference is we cannot really further reduce the mutual information to see the performance going down. This is because these are all natural kernel space that we can have. But in a synthesized way, we found that we can synthesize some other neural kernel space such that the mutual information for those kernel space are less than 5.4 here. So then you can see the performance starts to drop down. That forms the reverse U-shape. So you can see the mutual information here is really a key. And also, we also observe this such reverse U-shape for data augmentation. So like for most widely used data augmentation, kernel jittering for both the semi-clear paper and the MoCo paper, they somewhat twin the parameters. So we provide a full spectrum here. You can see that, so the parameter is the magnitude of kernel jittering. If you increase the magnitude, well, you have more heavier kernel jittering. Therefore, the mutual information between two independent augmentations are reduced. As you reduce the mutual information, the performance firstly get improved and then dropped. So you see a sweet spot here. And this is also similar for the random resized corp, where this parameter is the lowest threshold for your randomly resized corp. So the lower the threshold is, the more aggressive your data augmentation is. So as you can see, if you lower the threshold, you are have more aggressive data augmentation. The mutual information also keep decreasing, but the performance firstly improved and then dropped. So this is really also a sweet spot. And given the above observation and the informing principle, our question is really, can we synthesize effective views using some sort of learning approach? So as a starting point, we found this can be done actually. So we here provide a minimal prototype to show how this can be done. So firstly, we consider the problem from the kernel space perspective, such that the input X image is from an RGB space, and we want to have some invertible flow-based view generator to generate a novel kernel space. The way that we constrain it to be kernel space is the flow-based function only use one-by-one convolution. And of course, you stack multiple one-by-one convolution and redo structure together. So the flow-based view generator is a pixel-wise function. And because this function is invertible, it preserves all information stored in X. So you can imagine it's basically very similar to kernel space transformation. Pixel-wise function and provides the total information, preserves the total information. So therefore, this is a view generator that is a function parameterized by neural network, so you can learn it. And on top of these two views, you can learn an influence bound. So this is like an encoder trying to maximize the mutual information between them. So now this is a two-part. The first part is similar to the generator in GAN. And the second mutual information estimation part is similar to the discriminator in GAN. So therefore, the mutual information estimator is trying to maximize this INC bound. And your view generator is actually trying to adversarially attack it. So it's trying to generate views such as these views can minimize this bound. So this is an adversarial game between them. It's just a minimax game. Okay, so in that way, we hope that finally we can generate some views via the view generator such that the mutual information between the two views can be reduced. And this is, in this experiment, we found that actually you can definitely generate other neural kernel spaces which has less mutual information than this figure here. So this figure is like a YDBDR, and luminance and chrominance decomposition. So you can have neural kernel space that has less mutual information than this, and then you will see performance can be dropped. So that forms a complete reverse U-shape. But one drawback of this approach is it's not very stable. It's partly because it's GAN training. Firstly, it's GAN training. And another stuff is, well, it doesn't tell you how you should reduce the mutual information between the two views. It can be the case like most of the information can be squeezed into the second view, and the first view can just maybe contain just a little bit of information about the input. So in that sense, we found that this training is not very stable. It's not very stable in the sense that given the same amount of given the same parameter, same training recipe, you can result in views that have different amount of mutual information at the end. But it's still stable in that if you ensemble multiple runs together into one single plot, the reverse U-shape is stable there. So if you end up with a run that has less mutual information, it also might have a lower performance. So therefore, we came up with another approach, which is a semi-supervised approach. So we think, okay, in previous approach, when we want to just minimize the mutual information between the two views, which is the second principle of the informing principle. As a recap, the informing principle is trying to say, okay, we want to reduce the mutual information between V1 and V2. At the same time, we want each of the view to maintain necessary information for your downstream task. So for the adversarial approach here, it only reduces mutual information between the two views. It doesn't ask the two views to return information about your downstream task. So therefore, you can get a very weird views that doesn't perform well for your downstream task. That's expected. So for the second approach, we are assuming that you have a handful of labels for your downstream task. Therefore, you can build two classifiers on top of each of the view so that you hope you are trying to optimize the classifier at the same time. So in that way, you hope that you can, the induced classifier can help each of the view to maintain the information that is necessary about your downstream task. Okay. So the complete objective is the adversarial objective plus the two classification objective. So the view generator, for the view generator, it has two part of tasks. The first task is try to minimize the mutual information between V1 and V2 by playing the adversarial game with the encoder together. And the second task is try to, okay, the view generator and the classifier together, they will be optimized jointly to provide as higher accuracy as possible for those handful labels. So this is a semi-supervised approach. So for most of your samples, you can only play the adversarial game, but for a small amount of samples, you can also include the classification signal. And we found this approach makes the resultant view to be very stable. So in that case, if you run the system over multiple runs with the same parameter, you almost get the same set of views. So it's pretty stable in this time. And now we compare how this approach can improve the input views. So here, for this bar, suppose your input data is RGB, you can of course directly perform contrastive learning on the RGB data, and you get this accuracy. But then you can use the synthesize the views. So the RGB is here. You synthesize the views using the method that we just mentioned, and then you perform unsupervised contrastive learning on top of these two views, on top of the learned views, and you can see the representation get improved. The reason why the representation get improved is probably due to the informing guidance, such that the learned two views here, V1 and V2, they only contain information about your downstream task, but it doesn't contain other noise factors. So you can see that's how the improvement comes from. And at the same time, you can also have the input to be YDBDR, and you perform contrastive learning on top of YDBDR, or you learn two views on top of the YDBDR input, and you perform contrastive learning on the learned two views. And this gives you this gray bar. And you can see the learned views can be better than the original input. Okay, so that's the informing principle. Then beyond the unsupervised learning approach, I'm trying to also talk about two other works, which how you can think of the contrastive learning from a more general perspective. So as we said before, the self-supervised contrastive learning, the way you form positive pair is to use different augmentations of the same image. So the mutual information shared by the positive is quite a lot actually. Then we can think of this problem from another perspective. So suppose we know the labels of the images, then we can use images that are from the same classes to form positive pairs. So here, this dog and this dog, they belong to the same category, so they should be a positive pair and should be put together. So compared with the left side, where in the self-supervised learning setting, the dog image is different from this dog image, so they should be treated as negative. So you can see the difference here. So for the right cases, when you construct the positive pair in such a way, you can imagine the mutual information shared by this positive pair is only the dog label. So it somewhat falls into the informing story where in hope the two views, they only share the task relevant mutual information. So here is the dog label, but they don't share other specific image specific noise such as the background, different background, this stuff. So you can imagine this is the optimal views that you can have for contrastive learning if your downstream task is image classification. So what we do is then we firstly perform contrastive learning. This is stage one, just do normal contrastive learning. And of course, contrastive learning doesn't give you a classifier. So after you learn the backbone, then you freeze the backbone and you just train another linear classifier on top of the learned representation using labels. So only this part is learned in the second stage, only learn the linear classifier, okay? The backbone is only learned in the constructive stage. They are never jointly optimized, but you will find this approach can outperform the end-to-end cross entropy loss with many different networks. So here the purple line is the supervised contrastive approach that we have. And the other line is, the other three lines are cross entropy loss with different data augmentation. So you can see, actually for this ResNet 200, it might be around 0.5 or in our recent paper, we have even higher improvement, about 1% improvement over cross entropy baseline. So you can see that's some sort of significant improvement, especially on ImageNet benchmark. And another nice thing about the supervised contrastive learning is it really works well with the no data regime. So you can vary the percentage of the data you have from the ImageNet, and then you perform the compare supervised contrastive learning with cross entropy loss. And you can see supervised contrastive learning is better. And as for transfer learning, you can also compare supervised contrastive learning with other unsupervised contrastive learning, as well as cross entropy loss. So you transfer to CoCo dataset, and you can see it's also better. Okay, and the second thing is, the second stuff is contrastive representation, which is a work published in iClear this year. The thing is, in contrastive learning, we have two views, and this example is trying to demonstrate, okay, you can think of the two views in a more wider perspective. What can be the two views? Okay, so indeed, you can think of in knowledge distillation stuff, you are trying to transfer the knowledge from the teacher network to student network. And then you can formalize that problem as with a mutual information, such that mutual information maximization problem, such that you want to learn the student representation. that is trying to maximize its mutual information between the teacher network. And this can be solved by contrastive learning. So you can treat the representation from a teacher as a first view, and the representation from a student as a second view, and you perform contrastive learning there. And you can get a good performance, and get better performance than the original knowledge distillation. Okay, and for future works, and I think one perspective is you can have other novel view pairs, and you can apply contrastive learning to other modalities, such as point clouds, where you have plenty of unlabeled data. And you can also apply contrastive learning to graphs, and some people have already done that, I think. And another perspective is you can think about other new methodology. So this is a recent paper which is called Bootstrap Your Own Latent. So so in contrastive learning, one caveat is you really need to have large number of negatives. And in this Boyle paper, they are trying to remove the requirement of negatives. And they found that if you remove negative, you can get good performance. And if you add the negative, it only gives you small boost. The way that I view this paper is they have some sort of implicit contrastive learning actually. So you can imagine the denomination term in the contrastive noise is trying to say, okay, you are trying to scatter different, scatter the features of different images away, okay? Just a scattering effect. But in this paper, they have kind of many tricks to do that perhaps. For example, your backbone has batch normalization, and batch normalization is a natural way to scatter examples inside one single batch, right? So it's implicitly doing that. And another thing for this is they have an online network, which is updated also very slowly. But during the initialization of the online network will scatter the features, or just scatter the features uniformly to your unit sphere, to your feature space. So that online network also have the scattering effect. Okay, so probably I will stop here. And I was, a big thanks to my collaborators on this set of work. And probably I can take some questions now.
Yeah, thank you very